Okay, so welcome to the last lecture of the System Dynamics course, and today I would like to finish this example. It's a very important example. Yesterday we started this example, so I'm going to continue with that. But first, let's remember what we did yesterday. We're studying this system, which represents the roll dynamics of a missile. Aileron is used to control the rolling motion. This transfer function gives the roll rate, and the integral of the roll rate gives the roll position. So this is the open loop dynamics of the system. Okay, so if you consider the open loop transfer function between the aileron angle and the roll angle, it is given by the multiplication of these two transfer functions, and that gives times S plus B. This is the open loop transfer function. And if you look at the poles of the system, it is a second order system with one pole at the origin and one pole at minus B. And we know that we have a numerical value for B. B was given as 1. So this means we have this pole configuration for the open loop system. One pole here and another pole at the origin. Then we considered a feedback controller for this system. The feedback controller was given to be represented by this equation. And then we obtained, we drew the block diagram for the closed loop system. And the closed loop system transfer function turns out to be given by this function. So this is the closed loop transfer function. And in the closed loop transfer function, we still have two poles, but the pole locations now are different. In the open loop case, we had one pole here and then another pole here, but in the closed loop case, the two poles can be placed according to the values of these Kp and Kd values. And since these two free parameters appear, one for the constant term and one for the S term, this means that by choosing appropriate values for these two controller gains, these coefficients can be made whatever we want. And that means the closed poles can be placed arbitrarily. In fact, we also had found some expressions for that. If you choose, for example, a natural frequency and damping ratio for the closed loop system, then these controller gain values give us those closed loop poles. That means I can, for the closed loop system, I can choose any poles I want. This is the natural frequency. And the angle here is theta, and the cosine of that angle is the damping ratio. So let me write some explanation here. If you choose Kp and Kd values according to Onur'da, so there should be the mirror image of that as pole as well. Then the poles of the closed loop system can be placed anywhere on the complex plane. This type of controller design is known as the pole placement. And if you take the automatic control systems 2 course, AE483, the pole placement method is covered in that course. So anyway, so for certain types of systems, which this system is one of them, the poles can be placed arbitrarily. And okay, so let's now consider a sample design. Okay. Now let's consider a particular design with omega n is equal to 20 radians per second and zeta is equal to 0.8. And these numbers just come from how we want the closed system to behave like. Okay, so if you want to see the step response for these pole locations, I have that's plotted somewhere here. Okay, so this is the response of that system. Step response of the system with so this is how fast we want the missile to respond to a roll command. So the horizontal axis is time, the vertical axis is the roll angle. Okay, so if you remember the closed loop block diagram, I'm giving a desired roll angle command. Is there a magnitude there? So it is 10 degrees. Okay, so this is a plot in terms of degrees. So if I give a 10 degree roll command, then the actual roll angle changes according to this curve. And you see that it reaches steady state within about 0.3 seconds. Okay, so if you want to know the controller gains to give me these poles, they are given by these two equations, and the values are calculated here. Let me see. So these are the values for the controller gains. Bir tane not 4 oldu. Burada niye öyle oldu? Okay, so I was writing here, I think. So these are the controller gains. Okay, so everything is good so far. Now let me go back to Simulink. And now you know Simulink. You use Simulink in the lab, so I can show you some Simulink diagrams. Okay, so this is the open loop system. This is the missile roll dynamics. This is the integrator to get the roll angle. This was the open loop case, and I have a block diagram for the closed loop case as well, which is this diagram. So these are my controller gains, KP and KD. And if I execute this command, this simulation, that will give me so this is the angle response. As you can see, it reaches steady state again within about 0.3 seconds. Okay, now the problem gets interesting because, as I said, this comes from a real example, and in fact, I came up with this problem when I was designing an actual roll autopilot for Roketsan. So we were having some problems with the roll dynamics, and that's when I was studying this problem. So when you obtain this design in simulation, what you do next is you test this in a more realistic environment. Okay, so you perform like hardware in the loop tests or more advanced, more accurate simulation of the system. So this is the So let me put these blocks in a box. Okay, so this represents the missile. And let me put some labels here so that we can see what's going on. So this should be the aileron angle. This is delta A. This output is the roll rate, which we call P. And this is the roll angle. We use phi to represent that. And this part is the controller part, right? This is the autopilot part. This is the missile itself. So you test your design in simulation, and then you test in a more realistic simulation, right? So what you do there is you take this block out, and then you bring in another block which represents again the missile, but it may have some additional blocks to make to simulate the missile more accurately. So let me call this missile model, and let me call this more realistic. Çok küçük oluyor değil mi? Neyse. Okay, so we can add more additional blocks to this. For example, this is the aileron angle. Okay, and on an actual missile, when the autopilot creates the aileron commands, those commands are sent to the control actuation system, which is composed of some electric motors and gears, and that mechanism deflects the actual aileron. Okay, so they should be represented in our model if you want our model to be more accurate. So let me call this control actuation system, CAS. So in the simplest case, we can model this as a first order system. So let me model it as a first order system with a time constant of 0.1 seconds. Okay, so what does that mean? Model control actuation system with a transfer function like that, 1 over tau s plus 1, with tau is equal to 0.1 seconds. That means the following: if I give an aileron command of, let's say, 10 degrees, the actual aileron deflection will reach there exponentially, and how fast it takes that value depends on the time constant, right? So for example, it will take about 400 milliseconds to reach the 10 degrees, so which is a quite realistic model, in fact. Okay, so let me try this. So I took my simple missile model and placed there a more realistic model of the missile, which now includes the control actuation system. And this was the previous response. Now let me execute this new model and then see what I get. So as you see, the response is now unstable. Okay, so I give a step command. And as you see, the system gives an oscillatory response, and not only that, the oscillations grow in time and exponentially. So obviously, in my design, I used this simple model, and everything seemed to work fine. I thought I placed the poles to some very nice locations, but when I added just one simple first-order block to represent the control actuation system, the system became unstable. Okay, now this is the place where we can use the Routh-Hurwitz test to understand what's happening. So when we use this simple model for the missile and applied the feedback controller I showed yesterday, the closed-loop system becomes this, a second-order closed-loop system. And it has the pole locations in these places. Okay, but now what I did is I added an additional transfer function here. Okay, so which means I have an additional transfer function here. So obviously the closed transfer function is now different. In fact, even the order has changed, right? Because in the original system there were just 2 dynamic blocks here, giving us a second order system. Now we have 3 dynamic blocks, which means the order of the system must have been increased to 3. So the solution is given in the lecture notes. So let me just copy it here. With the above case model inserted, became unstable. And to understand what is going on, we need to look at the poles of the closed loop system with the case model inserted. So this is the new block diagram, and if you find the closed loop transfer function, this is what you get. Okay, so I'm just skipping all these steps, but you know how to find the closed loop transfer function using the given block diagram. So obviously the system is now third order. And let's find the poles of the new system, and there should be 3 of them, right? Okay, so let me just quickly calculate the poles here. Tau, and then I have b tau plus 1. And then I have b plus a times kd, b plus a times kd, and a times kp. because I need to define tau 0.1. And these are the 3 poles of the system, and obviously there's a pair of unstable poles, which explains the growing oscillations in the response. Okay? So obviously this autopilot design was not a good one, because we ended up with an unstable system when we had a counter-actuation system in the missile, which is obviously what we will always have. Okay, so this is the transfer function or the characteristic polynomial for the new third order system. We thought we placed the poles of the system to wherever we chose, but having unmodeled cast in the missile changed those locations. New pole locations depend on Kp, Kd, and tau, together with the open loop dynamics, together with A and B. To understand the relation between all these parameters, we can use the Routh-Hurwitz test. And that's given here. So if we apply the Routh-Hurwitz test, this is what we get. The test is performed in terms of the system parameters. So this is good because we can change them if we want to, right? So instead of using numerical values, it is better to leave them as these variables like Kd and tau and Kp, so that we can understand the importance of all these parameters on stability. Okay, so according to this test, there should be no sign changes here if you want a stable system, right? And all these terms should be greater than 0 for stability. So the first one is tau, time constant of the missile. It has to be positive if we are using a stable control actuation system. The second one says b tau plus 1 has to be positive. This is also automatically satisfied because tau is a positive number. B is coming from the missile transfer function. We know that there is positive as well, so this is also a positive number. A and Kp has to be positive. Okay, so that is positive as well, the control gain. So this must be violating the stability criteria. In fact, if we calculate the value of this quantity, we will find a negative number. Okay, so I don't want to spend time for doing that, but obviously this becomes it's a negative number. So positive, and switches to negative, switches from negative to positive. So two sign changes give us those two unstable poles. Now the question is, can I choose these Kp and Kd values better so that this is positive as well? And this equation allows me to do that, in fact. So let me go back to these lecture notes. Buraya bir açıklama yazayım. The third above array's first column becomes a negative number. This gives two sign changes and two unstable poles. So now, if I ask you, what should be the tau value so that the system stays stable, we can use that equation to find that. Using above equation, we can find the value of tau for which the system will stay stable with this chosen controller gains. So what I'm going to do is I'm going to use this relation. I'm going to enforce this value to be greater than 0. From here we can find an inequality for tau as, bütün bunların detaylı şu PDF dosyasında var bu arada. Yani you can refer to this PDF file if you want to find the details of this example. So this is a very nice application of this Routh-Hurwitz test. So this test tells me that if I know my missile dynamics, these B and A values, and if I have a controller design, these KP and KD values, then the system will be stable if tau was less than this critical value. And if you put in all the numbers here, you will find the critical value of tau to be 0.087 seconds. So this tells me the following. If I want to be able to use the controller I designed, autopilot, then I have to have a control actuation system which is, the time constant must be less than this value, which means I need to use a faster control actuation system. Okay? And if I do that, if I change my tau value, now tau was 0.1, if I change tau to, for example, 0.05, which is less than the critical value, the system will now become stable. So 0.1, I need to put so let me make this tau so that I can change it. Okay, so now let me execute it one more time. Okay, so now the response is really stable. And let me also convince you that that critical value we found for tau is really correct. So let me make tau so the critical value is 87 milliseconds. Let me set tau to just a little bit greater than that. Let me set the value of tau to 0.0 88, for example. So this is higher than the critical value. So I expect a slightly unstable system because it's just very close to the border of stability. And as you see that this is what I mean, this is slightly unstable. It is obviously unstable, but it grows rather slowly. And if I change the value to a number that is slightly less than the critical value, for example 0.86 milliseconds, then it should be stable, but on the verge of being unstable. And this is in fact what we get. So this is a stable system, but it oscillates a lot. So obviously this performance is, even though stable, far from what we expected, because in the design we thought we chose the pole locations very nicely, and the response we obtained for that was, where is that? So this is the response we expect, right? We expect the system to respond to roll angle commands without any oscillations and at this speed. What we get is stable, but far from our expected transient dynamics. So this is unfortunately what we get from the Routh-Hurwitz test. Since it only gives us stability information, yes or no information for stability, we find the boundary for stability. And obviously this is not an acceptable autopilot design. So you have to go back and change those Kp and Kd values to find a better response. But this is still good information. It at least tells us the critical value for the time constant. Okay, so if this is what you want to have, so you cannot compromise this time constant for the missile performance, then using this information you can go back and say we need a faster control actuation system for this missile. If you want this to be able to perform fast maneuvers, then the time constant has to be less than this value. In fact, it needs to be much less. So let me show that as well. Instead of, so if we can put a very, very fast control actuation system with time constant of this much, for example, 10 milliseconds, now we will see that the response will be much closer to our expected ideal response. See, this is pretty much our design response. Okay. Okay, so the example is still not over. There's just one final step, and that final step is in fact the most interesting part of this example. So after doing this analysis, I said, so obviously this tau is creating a problem, and this is what I have. I have this Routh test. Can I design an autopilot such that tau will not become a factor in stability anymore? That means, can I find Kp and Kd values for which the first column will always be positive no matter what tau is? So if I can find such a controller design, that means that controller will work for all possible control actuation systems, no matter how slow it is. And in fact, it turned out it is indeed possible. So, so the next question is, the closed-loop system will be stable for all possible values of tau. That means we know that this will always be positive. We're not worried about that. If we can make this third element positive, then we will achieve our goal. So the denominator is always positive, right? In fact, the denominator is already appearing here. We know it will always be positive as long as tau is positive. So if we can make this part positive, şimdi çok böyle monoton gittik de birazcık bunu düşünmenizi istiyorum aslında. Dedim ki bir otopilot tasarladım. Otopilotta aslında oldukça hızlı bir performans hedefledim. Değil mi? Yani saniyenin yarısından daha kısa bir sürede rol açısını, istediğim açıyı verebileyim gibi bir performans hedefim var. Bunun için çok hızlı bir control actuation sistem gerektiği ortaya çıktı ki mantıklı. Değil mi? Sen füze böyle hemen çok çabuk dönsün istiyorsan kanal çıkınında çok çabuk bükebilmen lazım. Şimdi diyorum ki control actuation sistem yavaş da olabilir. Yani öyle yavaş bir sistem var ki ben mesela 10 derece delta komutu verdiğim zaman o böyle yavaş yavaş dönecek ve hala sistem stable kalsın. Burada şeyi hissedebiliyorsunuzdur umarım. Eğer böyle bir şey hedefliyorsak şu performanstan feragat etmemiz lazım. Yani artık ben 0,3 saniyede istediğim açıya ulaşayım diye diretirsem bunu yapmamın şansı yok. Onu yapmanın tek yolu hızlı bir tağ kullanılması. Now the question is, I want the system to remain stable with even very slow control actuation systems, and obviously we need to make a trade-off, right? We need to give up on our performance requirements. But if you go back to the Routh array, from that test we can find some precise quantities. Okay, so you can read through this, but this is the critical part. If we choose Kp and Kd values such that this part is positive, then the inequality becomes the inequality changes sign. Instead of having an upper bound for the time constant, we obtain a lower bound for the time constants. Yani şuradaki şey şuydu, tau şu değerden küçük olacak diyorduk. Yani hızlı olması anlamına geliyor. Now since the inequality switches direction, the new inequality becomes this, which means the tau should be greater than some minimum time constant, which means the time constant or the control actuation system is slower than some critical value, and this critical value is a negative value. So this essentially means that and tau is negative, so the system will be stable for all positive tau values. The controller, in this case, we can say that it's infinitely robust to tau, and the condition for that is this. Okay, so let me. So if we choose such that is satisfied, the Routh test for stability for all positive values of tau. So this means I cannot choose Kp and Kd arbitrarily. I need to look for this inequality. And if you further play with that equation, and the details are given here, Bu da çok ilginç. Yani ekranda şurada yuvarlak görünüyor. Benim ekranımda bayağı basit bir elips olarak görünüyor. Ben bunu yuvarlak yapmaya çalışınca oradaki elips haline geliyor. Neyse. Ya burada bir sürü detay atlamak zorunda kaldım ama orada yapmamız gereken aslında çok atla deve değil yani. Şunlar vardı ya, KP ile KD için şu şeyler vardı. So if you use these relations in this inequality, now the inequality becomes in terms of omega n and zeta. From there you get some conditions for omega n and zeta. And that condition means that I have to choose the closed poles within this circle. Okay? And if I do that, the system becomes insensitive to tau value for stability. Okay? So when we first designed the autopilot, we placed some poles here, and we used these values. The omega was chosen at 200 radians per second, and zeta was 0.8. And these values are certainly outside that circle, right? The circle, this is 2. So the pole locations were chosen here, which gives a very fast response, and that becomes sensitive to tau. So if I choose these poles within this circle, obviously the response will be much slower because the omega n here has to be much smaller than the omega n for these poles. But the benefit is the system now becomes insensitive to tau values for stability. Okay. And now I think I can stop the recording.